Institute of Technology and Sciences, Visakhapatnam. Welcome to the course Communication Systems Engineering. Today we will discuss noise and noise performance of AM system. Because the noise is one of the important parameter which regulates the performance of communication system. So let us focus on the introductory part of the noise performance of communication system. So here I am defining the baseband system. So because this is useful for both the AM and FM systems. So noise can be divided into two parts. It may be external noise or internal noise. When it comes to internal noise, we can minimize the internal noise to some extent by proper design of the system. But external noise is not within our hands. So here I am focusing on the performance of the communication system, particularly in external noise. So let us focus on the baseband system, which has the transmitter, the communication media channel, the receiver system. So when it comes to the receiver, so it has both the incoming modulated signal as the receiving signal, and also external noise, which we can call it as NOT, white noise or Gaussian noise. Now, the performance of the communication system is basically defined in terms of the signal to noise ratio, because it is one of the important parameters to define the quality of the communication system, where we can define the quality in terms of the selectivity or fidelity. So let us focus on the signal to noise ratio calculation for baseband systems. Actually here what we need to determine the signal to noise ratio is the input signal and input noise, as well as the output signal and output noise. So from the input signal and noise contents, we can determine the input signal power as well as input noise power. So from the input signal power and noise power, we can find the input signal to noise ratio, that is SI by NI. Whereas from the output signal and noise components, S0 of T and N0 of T, we can determine the output signal power and output noise power. Later, we shall find the output signal to noise ratio as S0 and N0. So this input signal to noise ratio and output signal to noise ratio is common for all modulation systems. That is, it may be AM system or DSPSC modulated system or SSPSC modulated system or vestigial sideband or frequency modulated system. So now I will switch on to the signal to noise ratio calculation for AM system. So here, before attempting the signal to noise ratio for AM system, let us focus on the difference between the noise figure or noise factor and the figure of merit. When it comes to noise figure or noise factor, it is the ratio of input signal to noise ratio to output signal to noise ratio. Whereas the figure of merit is the ratio of output signal power to noise power to the input signal power, input noise power. So let us switch on to the noise calculation in AM system. So just recollect the baseband system and redefine the baseband system block diagram for AM signal or AM modulated system. So here, if you observe the basic block diagram of the noise calculation in AM system, it has the band pass filter and envelope detector. When it comes to the input side of a receiver system, the receiver receives the amplitude modulated signal as well as the noise which we are defining in terms of the white noise or Gaussian noise. So the significance of band pass filter here is to minimize the noise to some extent, which avoids the problem of the envelope detector or which increases the performance of the receiver system. Here I am using the band pass filter. So when you observe the output of the band pass filter, which is defined in terms of SI of T and NI of T, nothing but the output signal and the band pass noise. That means the difference between the band pass filter input and band pass filter output is, when it comes to input, I am calling it as the white noise or Gaussian noise. So when it comes to the band pass filter output, so it is the band pass noise. The difference is that the noise or white noise will be again minimized to some extent using the band pass filter. So the inputs to the envelope detector are SI of T and NI of T. Now from these two parameters, I am trying to calculate the input signal power and input noise power. So before obtaining the input signal power and noise power, let us focus on the input signal along with the noise. the signal here is the amplitude modulated signal, which is defined as AC cos omega ct into 1 plus Km of t. The noise is nothing but the white noise defined as NW of t. So the input to the demodulator or detector is AC cos omega ct into 1 plus Km of t plus the band pass noise Ni of t. So that means the equation 2 has two terms. The first term is the signal component and the second term is the input noise or band pass noise. So from the signal component, try to determine the input signal power SI, which is nothing but the mean square power. So that is defined as AC square by 2 into 1 plus Ka square m square bar t. So from the band pass noise Ni of t, the noise power is defined as capital Ni equal to Ni square t bar. So from the input signal power SI and noise power Ni, try to calculate the input signal to noise ratio SI by Ni. Now, before determining the output signal power to noise power, let us focus on the envelope detector. So the envelope detector detects the envelope of the actual message signal from the amplitude modulated signal. So try to define the envelope of the modulated signal. Now in order to define the envelope of the modulated signal, once again I am redefining the modulated signal, amplitude modulated signal along with the noise component. That is nothing but AC cross omega ct into 1 plus Km of t plus the noise has both in phase component and quadrature component. That is NC of t and NS of t. From that equation, try to define the envelope as AC into 1 plus Km of t plus NC of t square plus other component, that is quadrature component, as NS square t power 1 by 2. So let us focus on the small noise and large noise case in case of amplitude modulated systems. Compared to DSPSC modulated system, amplitude modulated system has additional carrier. So here I am considering two types of noise named as small noise as well as large noise. Now let us focus on small noise. In case of small noise case, the noise component Ni of t is very small compared to the signal, that is AC into 1 plus Km of t. So or otherwise, the signal is much greater than either in phase noise component or quadrature noise component. So from that approximation for small noise case, let us redefine the envelope of the system or envelope of the envelope detector, that is AC into 1 plus Km of t square plus 2 AC 1 plus Km of t into NC of t. Here, when noise is small, the other two components will be disappear. That means we can neglect the other noise components. Now, from this equation, take this AC into 1 plus Km of t as a common parameter. So I can define it as AC 1 plus Km of t into 1 plus 2 times NC of t divided by AC into 1 plus Km of t power 1 by 2. So as the case itself says, the noise is small. Whenever I focus on the ratio in the second term, the term itself is small. Now I am assuming this as x. So when NC of t is small, the whole ratio x is very small. So I can redefine this equation as 1 plus x by 2. So try to redefine the equation now. So the term AC into 1 plus Km of t into 1 plus x by 2. Oh, no, the envelope is AC into 1 plus Km of t into the rest of the term, which is defined in the bracket. After simplification, I am getting the envelope as AC into 1 plus Km of t plus NC of t. Now from this equation 9, it is clear that the envelope has both signal component and noise component, which is defined as the output of the envelope detector. Now from this equation 9, try to define the signal power and noise power as S0 and N0. From S0 and N0, try to define the output signal to noise ratio. Now, if we consider the overall signal to noise ratio, which is defined as the figure of merit, that is output signal to noise ratio to input signal to noise ratio. After simplification, it gives 2 times Ka square m square t bar divided by 1 plus Ka square m square t bar. Here, m square t bar defines the mean square signal power. M of t is nothing but a message signal, so m square t bar is nothing but the mean square signal power or mean square message signal power. Now, redefine the equation, and here substitute the mean square power of the input message signal. So, overall signal to noise ratio figure of merit becomes 2Ka square AM square by 2 divided by 1 plus Ka square AM square by 2. So, here Ka is the amplitude sensitivity, which is nothing but 1 by AC. By substituting and simplifying that expression, we can get the overall signal to noise ratio as 2 times AM square by AC square divided by 1 plus AM square by AC square. Here AM by AC is nothing but a modulation index. So I am replacing this with mu or small m. So 2 mu square divided by 1 plus mu square. But here this is the noise calculation for amplitude modulation systems. Hence the modulation index for amplitude modulation system is 100%. So replace that modulation index mu by 1. I can redefine the figure of merit or overall signal to noise ratio as 2 times 1 divided by 2 plus 1, that is 2 by 3. So this is the figure of merit of AM system for small noise case. On the other side, if you consider the large noise case, the case itself says the noise is very much large compared to the signal. Hence, the bandpass noise Ni of t is very much greater than the signal component, or either the in-phase noise or quadrature noise component of the amplitude modulation system with the noise is much greater than the signal component. So now by considering this approximation, I am defining the envelope. At the end, what I obtain is by assuming these two terms nc square t plus ns square t as r of t, I am defining the envelope as r of t into 1 plus 2 ac nc of t into 1 plus km of t divided by r square t power 1 by 2. Here, what I am considering is, whenever I am taking r of t as a common factor, the envelope equal to r of t into 1 plus ac and c of t into 1 plus km of t divided by r square t. Now redefine this envelope for simplification. That is, envelope is approximately equal to r of t plus ac and c of t into 1 plus km of t by r of t. Now here, further you can simplify this envelope by considering the Phasor diagram. When you focus on the Phasor diagram of the amplitude modulation system, this ratio nc of t by r of t can be defined in terms of the Phasor diagram parameters which is involved with cos theta. So r, from this expression I can say that the noise is more in the denominator. When the noise is more in the denominator, the envelope can be further approximated. Or otherwise, for large noise case, this noise is no longer additive with the message signal. That means we cannot separate the message signal and noise. So, from the envelope, I could not recover the message signal alone. So, which I can call it as threshold effect. That means, under large noise case, we cannot separate the noise and message because both are not additive in nature. So, this effect is called as threshold effect. So, this is Dr.B.Somasekhar, Associate Professor, Department of ECE, Untitled Institute of Technology and Sciences, Visakhapatnam. Welcome to the course Communication Systems Engineering. Today we will discuss noise and noise performance of AM system. Because the noise is one of the important parameter which regulates the performance of communication system. So let us focus on the introductory part of the noise performance of communication system. So here I am defining the baseband system. So because this is useful for both the AM and FM systems. So noise can be divided into two parts. It may be external noise or internal noise. When it comes to internal noise, we can minimize that internal noise to some extent by proper design of the system. But external noise is not within our hands. So here I am focusing on the performance of the communication system, particularly external noise. So let us focus on the baseband system, which has the transmitter, the communication media channel, the receiver system. So when it comes to the receiver, so it has both the incoming modulated signal as the receiving signal and also external noise, which we can call it as N of T, white noise or Gaussian noise. Now, the performance of the communication system basically defined in terms of the signal to noise ratio, because it is one of the important parameters to define the quality of the communication system, where we can define the quality in terms of the selectivity or fidelity. So let us focus on the signal to noise ratio calculation for baseband systems. Actually here what we need to determine the signal to noise ratio is the input signal and input noise as well as the output signal and output noise. So from the input signal and noise contents we can determine the input signal power as well as input noise power. So from the input signal power and noise power we can find the input signal to noise ratio, that is SI by NI. Whereas from the output signal and noise components S0 of t and N0 of t, we can determine the output signal power and output noise power. Later we shall find the output signal to noise ratio as S0 and N0. So this input signal to noise ratio and output signal to noise ratio is common for all modulation systems. That is, it may be AM system or DSPSC modulated system or SSPSC modulated system or vestigial sideband or frequency modulated system. So now I will switch on to the signal to noise ratio calculation for AM system. So here, before attempting the signal to noise ratio for AM system, just let us focus on the difference between the noise figure or noise factor and the figure of merit. When it comes to noise figure or noise factor, it is the ratio of input signal to noise ratio to output signal to noise ratio, whereas the figure of merit is the ratio of output signal power to noise power to the input signal power to input noise power. So let us switch on to the noise calculation in AM system. So just recollect the baseband system and redefine the baseband system block diagram for AM signal or AM modulated system. So here, if you observe the basic block diagram of the noise calculation in AM system, it has the band pass filter and envelope detector. When it comes to the input side of the receiver system, the receiver receives the amplitude modulated signal as well as the noise which we are defining in terms of the white noise or Gaussian noise. So the significance of band pass filter here is to minimize the noise to some extent, which avoids the problem of the envelope detector or which increases the performance of the receiver system. Here I am using the band pass filter. So when you observe the output of the band pass filter, which is defined in terms of SI of t and NI of t, it is nothing but the output signal and the band pass noise. That means the difference between the band pass filter input and band pass filter output is, when it comes to input, I am calling it as the white noise or Gaussian noise. So when it comes to the band pass filter output, so it is the band pass noise. The difference is that the noise or white noise will be again minimized to some extent using the band pass filter. So the inputs to the envelope detector are SI of t and NI of t. Now from these two parameters I am trying to calculate the input signal power and input noise power. So before obtaining the input signal power and noise power, let us focus on the input signal along with the noise. The signal here is the amplitude modulated signal, which is defined as AAC cos omega ct into 1 plus KAM of t. The noise is nothing but the white noise defined as NW of t. So the input to the demodulator or detector is AC cos omega ct into 1 plus KM of t plus the band pass noise NI of t. So that means the equation 2 has two terms. The first term is the signal component and the second term is the input noise or band pass noise. So from the signal component, try to determine the input signal power SI, which is nothing but the mean square power. So that is defined as AC square by 2 into 1 plus KA square M square bar T. So from the band pass noise NI of T, the noise power is defined as capital NI equal to NI square T bar. So from the input signal power SI and noise power NI, try to calculate the input signal to noise ratio SI by NI. Now, before determining the output signal power to noise power, let us focus on the envelope detector. So the envelope detector detects the envelope of the actual message signal from the amplitude modulated signal. So try to define the envelope of the modulated signal. Now in order to define the envelope of the modulated signal, once again I am redefining the modulated signal, amplitude modulated signal along with the noise component. That is nothing but AC cross omega CT into 1 plus K M of T plus the noise has both in phase component and quadrature component. That is NC of T and NS of T. From that equation, try to define the envelope as AC into 1 plus K M of T plus NC of T square plus other component, that is quadrature component, as NS square T over 1 by 2. So let us focus on the small noise and large noise case in case of amplitude modulated systems. Compared to DSPSE modulated system, amplitude modulation system has additional carrier. So here I am considering two types of noise named as small noise as well as large noise. Now let us focus on small noise. In case of small noise case, the noise component Ni of T is very small compared to the signal, that is AC into 1 plus Ka M of T. So or otherwise the signal is much greater than either in phase noise component or quadrature noise component. So from that approximation for small noise case, let us redefine the envelope of the system or envelope of the envelope detector, that is AC into 1 plus Km of T square plus 2 AC 1 plus Km of T into NC of T. Here when noise is small, the other two components will be disappear. That means we can neglect the other noise components. Now from this equation, take this AC into 1 plus Km of T as a common parameter. So I can define it as AC 1 plus Km of T into 1 plus 2 times NC of T divided by AC into 1 plus Km of T power 1 by 2. So as the case itself says, the noise is small. Whenever I focus on the ratio in the second term, the term itself is small. Now I am assuming this as X. So when NC of T is small, the whole ratio X is very small. So I can redefine this equation as 1 plus X by 2. So try to redefine the equation now. So the term AC into 1 plus Km of T into 1 plus X by 2 power 1 by 2. Now the envelope is AC into 1 plus Km of T into the rest of the term which is defined in the bracket. After simplification, I am getting the envelope as AC into 1 plus Km of T plus NC of T. Now from this equation 9, it is clear that the envelope has both signal component and noise component, which is defined as the output of the envelope detector. Now from this equation 9, try to define the signal power and noise power as S0 and N0. Now from S0 and N0, try to define the output signal to noise ratio. Now if we consider the overall signal to noise ratio, which is defined as the figure of merit, that is output signal to noise ratio to input signal to noise ratio. After simplification, it gives 2 times Ka square M square T bar divided by 1 plus Ka square M square T bar. Here M square T bar defines the mean square signal power. M of T is nothing but a message signal. So M square T bar is nothing but the mean square signal power or mean square message signal power. Now redefine the equation and here substitute the mean square power of the input message signal. So overall signal to noise ratio figure of merit becomes 2 Ka square Am square by 2 divided by 1 plus Ka square Am square by 2. So here K is the amplitude sensitivity, which is nothing but 1 by AC. By substituting and simplifying the expression, we can get the overall signal to noise ratio as 2 times Am square by AC square divided by 1 plus Am square by AC square. Here Am by AC is nothing but a modulation index. So I am replacing this with mu or small m. So 2 mu square divided by 1 plus mu square. But here this is the noise calculation for amplitude modulation systems. Hence the modulation index for amplitude modulation system is 100%. So replace that modulation index mu by 1. I can redefine the figure of merit or overall signal to noise ratio as 2 times 1 divided by 2 plus 1, that is 2 by 3. So this is the figure of merit of AM system for small noise case. On the other side, if you consider the large noise case, the case itself says the noise is very much large compared to the signal. Hence, the bandpass noise Ni of T is very much greater than the signal component, or either the in-phase noise or quadrature noise component of the amplitude modulation system with the noise is much greater than the signal component. So now by considering this approximation, I am defining the envelope At the end, what I obtain is, by assuming these two terms, NC square t plus NS square t as R of t, I am defining the envelope as R of t into 1 plus 2 AC NC of t into 1 plus km of t divided by R square t power 1 by 2. Here, what I am considering is, whenever I am taking R of t as common factor, the envelope equal to R of t into 1 plus AC and C of t into 1 plus km of t divided by R square t. Now redefine this envelope for simplification. That is, envelope is approximately equal to R of t plus AC and C of t into 1 plus km of t by R of t. Now here, further you can simplify this envelope by considering the phasor diagram. When you focus on the phasor diagram of the amplitude modulation system, this ratio NC of t by R of t can be defined in terms of the phasor diagram parameters which is involved with cos theta. So R, from this expression I can say that the noise is more in the denominator. When the noise is more in the denominator, the envelope can be further approximated. Or otherwise, for large noise case, this noise is no longer additive with the message signal. That means we cannot separate the message signal and noise. So, from the envelope, I could not recover the message signal alone. So, which I can call it as threshold effect. That means under large noise case, we cannot separate the noise and message because both are not additive in nature. So, this effect is called as threshold effect.